Let's talk about neural networks. Without going into more detailed topics about the design and optimization of neural networks and deep learning, we discuss the motivation and background surrounding neural networks along with basic architecture choices. We will try to see how neural networks came around, what are they, why neural networks are called neural networks, how do they actually work, how do they learn, and most importantly, how can we use neural networks in practice for our machine learning projects. Let's start by looking back at linear regression from a slightly different perspective, that is, concentrating on the information flow, information processing from input to the output. Speaking of input and output, linear regression basically assumes a linear relationship between input variable x1, x2, and so on, and the single output variable y, like shown here by the linear regression equation. Let's see now how all this looks if we draw a diagram to visualize what's going on here. That is, given some inputs, two shown here for simplicity, x1 and x2, along with the bias 1, linear regression takes the inputs weighted accordingly by the weights w0, w1, and w2, sums up all these weighted inputs, and examines this weighted sum at this big blue unit here, and well, does nothing to the sum other than just passing it along to the output, O. If this linear regression output O is not matching the target value, y, then based on how large the error y minus output is, the weights w0, w1, and w2 are adjusted so as to make the linear regression produce better outputs closer to the target value and reducing the error. Doing this several times until better and better w0, w1, and w2s are learned from the training data for a more reliable model that we can later use to make predictions with. Now, for the slightly different perspective, let's look closer at the big blue intermediate information processing unit, let's call it, connecting the input to output, where the actual weighted sum arrives and leaves unchanged, or should we rather say arrives and leaves, quote-unquote, changed by the identity or linear function, that is, f of x equals x. In machine learning, this function is actually known as the activation function. We'll soon see why. Moving on to the logistic regression now, examining its information flow mechanism from the same perspective, we notice that it has a strikingly similar structure with a nonlinear activation function, the sigmoid, at its blue processing unit. The weighted sum arrives at the incoming chamber of the processing unit. It's first processed by the sigmoid activation function, and the processed weighted sum is then passed from the outgoing chamber to the output of the network, of the structure here. If the output is not matching the target class, learning the logistic regression model is very similar to learning the linear regression, right? We change the weights until the logistic regression outputs match the actual target. A short note here, it's a fairly simple nonlinear function, the sigmoid activation function, but it also has easily to calculate derivative, which can be very important on calculating the weights updates for the gradient descent. Can this pattern go on? Yes. Very much like logistic regression, this so-called Perceptron uses another nonlinear activation function at its blue unit processing unit, this time a step function, to also solve binary classification problems for, this time, classes +1 and -1. Unlike the logistic regression, though, the Perceptron activation function, the step function, is not differentiable everywhere, so the Perceptron's weights w0, w1, and w2 are not learned by gradient descent. Without going into much detail again, a method for learning the weights of the Perceptron from data, called Perceptron's algorithm, was introduced by the psychologist Frank Rosenblatt in 1957, the basic principle being very similar to gradient descent, without computing derivative, that is, but rather leveraging samples and weights vector products signs, plus or minus 1, at what with a classification target plus or minus 1. That's one of the reasons the classification classes here are called plus minus 1 instead of 0 or 1, to carry the sign of the dot product. Although the Perceptron classification algorithm is a more basic procedure, the Perceptron is considered one of the important pioneering units of artificial neural networks, as the idea behind this thresholded Perceptron was to mimic how a single neuron in the brain works. It either fires or not based on the information received. Similarly, a perceptron received multiple input signals, and if the sum of the input signals exceed a certain threshold, it either returns a signal or remains silent. While a pioneering concept, its basic structure and activation function restricted perceptron success, and therefore neural network success at the time, to mostly linearly separable datasets. So perceptrons, or neural networks, fell out of grace for a while after first implementation and applications in the 1960s. Until the late 1980s, that is, when research on neural networks regained strength and neurons with more differentiable activation function shapes started to be considered, like sigmoid or hyperbolic tan or the most popular ReLU, and the possibility of differentiating the activation function along to use of gradient descent for weights adjustment improved the neural network performance or other datasets. And this is what we call an artificial neuron, designed to mimic aspects of its biological counterpart, the neuron in the brain, or at least what at the time was believed about how neurons in the brain function, receiving inputs from the surrounding that activates and responds from the neuron to then send out an output. Keep in mind that in fact, cyberneticists and neurophysiologists McCollum and Pitts began to develop models of artificial neurons as early as 1943. While there are quite a few differences between artificial neurons and how biological neurons might function, the name stayed. Okay, so now that we know that what an artificial neuron is, basically this processing unit receiving weighted information and inputs that's being processed, analyzed somehow, ideally non-linearity, to show some processing, and handed over, how to get beyond one unit or one neuron, and more importantly, why? As we have mentioned, a limitation of the perceptron or artificial neuron is that it captures mostly linear interactions in the data. So the question is, can we use a similar approach to capture non-linear interactions in the data? For example, this historically famous example of XOR problem, given these 4 XOR data points, blue circles and orange triangles, separate the blues from the orange inputs using the concept of an artificial neuron. Now, one artificial neuron, as we see it here on the left, right, our artificial neuron here on the left, it's only capable of separating data with a single line. And unfortunately, the XOR data points are not linearly separable. That is, any line you'd consider would not completely separate the blues from the oranges. Unless, of course, you'd consider 2 lines, that is, 2 neurons working together to get the job done. Each of these 2 neurons sending its output to another neuron, which weights the inputs coming from these 2 neurons to make the final class decision. This architecture, with the right set of weight values, is capable of nonlinear separation, and it can provide the necessary separations to actually separate or classify our XOR data point. And this is what we traditionally called multilayer perceptron, or also famously known as neural networks. Adding more neurons created a new layer between the input and the output, a new layer known as the hidden layer. It's hidden from the outside, basically connecting to the outside only through the input and the output. So let's start thinking of the neural networks as having an architecture composed of layers. The input layer consisting of just the data inputs, the hidden layer that receives the weighted inputs and has an activation function, and whose outputs could be used as the inputs to other layers of neurons. And finally, the output layer, also having an activation function that produces the output of the whole network. Also, each layer is connected to the next. That is, the neurons of a given layer get inputs from neurons on the previous layers and feed their outputs to the next. These are usually called dense layers or fully connected layers. Only the hidden and the output neurons have an activation function, and therefore only those are deemed as neurons layers per se, And so the neural network here is traditionally described as a two-layer neural network. One hidden layer with two neurons inside, and one output layer with one neuron. Similarly, linear regression, logistic regression, and Perceptron can be viewed as single-layer, single-neuron neural networks, or simply called single-layer neural networks. Now, speaking of the architecture of neural networks, this is truly very high level and basic stuff on neural networks. So for more details beyond input, hidden, output layers, and activation functions, please check out this link to the d2l.ai online textbook for more details. However, worth noting, the number of weights increase from one neuron single layer single neuron networks to this one. We used to have W0, W1, or W2, meaning like 3 weights for the one neuron network. Now we have 6 plus 3, that's like 9 different weights. Or for a 2-layer network with 4 neurons in the hidden layer, so just adding 2 more neurons, we have 12 plus 5 equals 17 weights, almost double from the previous 9. With adding more neurons in the hidden layer or in the output layer, or even more hidden layers altogether, the number of weights grow fast. And things don't stop here. As I said, having a neuron with 2 neurons, having a network with only 2 neurons in one hidden layer is not particularly useful for most real-life machine learning applications. So typically, we use more complex neural networks to approximate more complex functions that cannot be easily described by traditional methods. The trick is to design or engineer a network architecture to your task at hand. For more complex binary classifications, for example, maybe more patterns in the data to be learned, to do a better job separating the classes, we could design something like the top left network here, with 5 neurons in the hidden layer. Or multi-layer networks like the one on the right, with 4 layers, of which 3 are hidden layers with 5, 3, and 2 neurons respectively, and 2 neurons in the output layer. Of course, depending on the problem to be solved, we can go much deeper than 4 layers. And we just demystified deep learning right here. More and more hidden layers make for deeper networks, more flow and more analysis of information received from the inputs in the way to their outputs and connected to the outputs, making more and more networks more capable of more capable learners altogether. Now, for a free class classifier, we could design something like the network on the bottom left here, with 5 neurons in the hidden layers and 3 neurons in the output layer, one output neuron generating the probability of class for each class. Now, as you might guess, for even more complex tasks, say higher dimensional tabular data sets or image data or text data, more complex architectures can be and has been engineered, like the so-called convolutional neural networks. They are neural networks engineered to better learn from image-like data, or recurrent neural networks engineered to better learn from sequential data. They work very well on text, to name a few. For more details on this and beyond and more, please check out again the link to the d2l.ai online textbook. For now, let's try to better understand what's needed to build and train a fit-for neural network, say on a binary classification task with no bias included for simplicity. So let's build and train a simple 2-layer neural network with 2 neurons in the hidden layer and 1 neuron in the output layer. By the way, different choices of number of layers or number of neurons inside each layer might work better for a given task. So these are hyperparameters of the neural networks that you're trying to build and need to be tuned on a validation or, with some cross-validation techniques. We also need to equip our neurons, our 3 neurons here, with activation functions. So let's have a look at a few choices. Commonly used activation functions include sigmoid function, the tan hyperbolic function, and the ReLU function. The sigmoid function is a popular activation, often called a squashing function, because it squashes any number, every real value number between the range of 0 and 1. For that very reason, in the earliest neural networks, scientists interested in modeling biological neurons, which either fire or don't, reached out to sigmoid as a natural choice for an activation function. When attention shifted to gradient descent-based learning, the sigmoid function was a winner again because it has a very easy to compute derivative. So sigmoid are still widely used as activation function mostly at the output units when we want to interpret the outputs as a binary classification problem, a probability of a binary classification problem. However, they are not as popular in the hidden layers. They've been replaced by more trainable and simpler ReLU functions. Now, the hyperbolic tangent, like the sigmoid function, it's used to squash any numerical value between now the range -1 plus 1. And note that also near 0, just like the sigmoid function, the tan function actually approaches a linear transformation, a linear function. And the other thing that's a little bit different from the sigmoid function is that although the shape of the function is similar with the sigmoid one, the tan function exhibits a point symmetry not around 0.5 but around 0. Now for the last one here, the rectified linear unit, the last activation function, it's actually the most popular choice nowadays since like 2011 due to both simplicity of implementation and its performance on a variety of predictive tasks. It's a very simple nonlinear transformation, basically retaining only positive elements and discarding all negative elements, setting the corresponding activations basically to 0. All these activation functions have very easy to compute derivatives, which makes them very easy to use for gradient descent based learning. So now let's have a look at some options of output activation functions. We mentioned the sigmoid, right, which is a very popular choice for binary classification problems, as the output value between 0 and 1 that can be interpreted as probabilities for each class. So, for example, if you have an output value of 0.89, they will suggest that 89 chance the data point belongs to class 1 and 11% chance that that data point will belong to class 0. Now, for multi-class classification problems, there is softmax, also known as the normalized exponential function, which extends the sigmoid to multi-class classification. It's a function that basically normalizes the outputs to the scale 0 and 1 and ensures that those outputs sum up to 1 as well. This is what dividing the exponentials by the sum of all does here. So if we take an example of a free class classification problem for given a free output neurons like we've seen on the previous slides, softmax would output for each neuron at value between 0 and 1. Think of it as one class probability for each class that we have in there. And the sum of all these free probabilities will add up to 1, just like with the two classes. Out of these free probabilities, the highest will decide the final class predictions, just like in the two-class scenario. Now, for regression, a very good choice of an output activation function is the linear function, as seen with the linear regression, or a ReLU sort of function if the negative values are of no interest. So let's complete our network build here, deciding to have all our free neurons use a sigmoid activation function. And by the way, different activation functions, either at the hidden layers or at the output layers, can be chosen for different layers. Don't need to be the same, although all the neurons inside the same layer will use the same activation. But otherwise, the activation functions are also hyperparameters of your neural network, so again, they need to be tuned by using either a validation set or some sort of cross-validation. Now, to keep us organized and in general for easier to follow computations, notice the notations here. The first neuron in the hidden layer is called H1, the second one H2, and O for the output neurons, each with their own upper scores in and out to represent the incoming and outgoing values at that particular neuron. So one last thing, with given inputs, x1 equals 0.5 here and x2 equals 0.1 here, in order to pass forward these inputs through the network, we need to start with some initial values for all our weights, 6 weights here. This is what traditionally is called initializing the network. Have to start somewhere, take a guess, and if that guess is not good, we'll adjust course as needed. Just like with the activation on output functions, in practice, there are also some popular ways to initialize neural networks that you can pick from or create your own. So add that to your list of neural networks hyperparameters. Now let's assume, for the example here, we assume the values listed at the top for W1 through W6, all our weights. So now we really have all we need to push those two inputs through the network and compute the network output based on these two inputs. Something like this. Let's first move from the input layer to the hidden layer. With the inputs being 0.5 and 0.1, the weighted sum arriving at the first hidden neuron, age 1, that will be age 1 in, according to the values here, turns out to be 0.15 times 0.5 plus 0.25 times 0.1, and it ends up to be 0.1. This weighted sum will then be transformed by the sigmoid activation function into 0.52. Similarly, at the second neuron in the hidden layer, with the inputs 0.5 and 0.1, the weighted sum arriving at the second hidden neuron will be 0.13, and the output value will be 0.53. These output values from the first layer, 0.52 and 0.53 respectively, they will be the inputs to the next layer's neuron. So let's keep going. One more pass forward through the network is needed. You can imagine how this might be going for longer or much deeper neural networks or architectures. So moving through the hidden layer, from the hidden layer to the output layer, let's first compute the weighted sum arriving in the output at the output neuron from its inputs coming from those two hidden neurons. That is O superscript in, according to the values here, will be 0.52 coming from the first neuron, a hidden neuron, times 0.4 plus 0.53 coming from the second hidden neuron times the weight, 0.45. It turns out to be 0.44. Now this weighted sum is also going to be transformed by the sigmoid activation of the output neuron, and it's computed to be 0.61. This is the final output of your network, right? Using a decision boundary at 0.5 for binary classification purposes, we would classify this as class 1, as 0.61 is more than 0.5. Now, if the true class of your input data point, which is 0.5, 0.1, is indeed 1, we were very lucky, right, and built a very good neural network in the first try. Most of the time, however, the first model or the first neural network we build might not get it right, the class prediction, that is. So if the output didn't match the target, given this neural network architecture, the number of layers, the number of inputs, the activation functions, and so on, if the output didn't match the target, given this neural network architecture, the neural network weights will have to change such that the error arriving, error obtained between the output and the true value target, the target gets smaller. So how would you do that? Well, I think we heard the storyline before, right? Will be something. I mean, it's actually the gradient descent. We'll have to push the model in the opposite direction of the error's gradient, one step at a time, to minimize the model's error. Now, how to compute this error function, because we haven't talked about it yet, so we can actually go ahead and adjust all the weights or adjust the model accordingly. So here are a few choices of error cost function, also called cost functions, that can be used to basically compare the neural network outputs with the truth with the desired target. For binary classification, log loss, also known as the cross entropy for logistic loss, it's a numerical value that measures the performance of the binary classifier when the model output its a probability between 0 and 1. There is a similar loss function called cross entropy for softmax loss that can handle multi-class classification. It basically just extends the cross entropy for logistic loss beyond two classes to multi-class, right? Where I, it's here the class index. Whereas for regression, the popular mean square error, which is the average of the sum of square errors, it's really a popular choice and is to-go choice for measuring the error of regression models. Note again that all these error functions are differentiable, desired property, if we want to go ahead and apply gradient descent to update the model or the model weights. And finally, with an appropriate selected cost function, we have all we need to update all neural networks weights automatically through a process known as back-propagation, that is basically applying a gradient descent update to every weight of the neural network. Like this. Adjust the old value of a weight to a new value of the weight by using a so-called learning rate and the gradient of the cost function with respect to that weight. Now add the learning rate to your bag of neural networks hyperparameters, as different values of this learning rate might help your neural network learn better, faster, more efficiently. So to recap training neural networks here, after settling on a neural network architecture, the back-propagation algorithm begins by comparing the actual neural network output by forward-propagation to the expected value of the target, and then moves backward through the network, slightly adjusting each of the weights in the direction that reduces the error by a small degree. Both forward and back propagation are rerun hundreds or thousands of times on each input combination until the network can accurately predict the expected output of the possible inputs using the forward propagation. While more goes on underneath all these processes, again, please check the link for more details. A final note on these neural network trainings. Learning neural networks or their weights thereof is to make the network produce better outputs closer to the actual target. Keep in mind that these networks tend to be very large. Some of the largest networks have contained hundreds of billions of weights or so-called network parameters. So optimizing them can be a very daunting task and requires massive amounts of computing power. The large size of neural networks is one reason behind this neural network-specific regularization technique to prevent overfitting. While L1 and L2 regularizations are still valid options for neural networks, keep in mind that L1 and L2 work on all the weights at the same time, and there are many weights in the neural networks. So L1 and L2 regularizations are not as popular with neural networks. A better way to regularize neural networks is to take some of the weights out of the network altogether, forcing the other ones to pay more attention, learn better from the inputs, and to correctly match the output. Randomly removing some nodes with a fixed probability during the neural network training will achieve this. Now, because of the outputs of the layer and the dropout are randomly subsampled, it has the effect of thinning the network during training. As such, a wider network, meaning more nodes, may be required when using dropout. Dropout is only one of the many other techniques developed to improve neural network learning from data. They are not the scope of this accelerated dive into ML. So for more details on dropout and beyond, please follow the link here or join back for more in-depth courses on neural networks and deep learning. And that's because after a bumpy start in the 1960s and 1980s, neural networks are here to stay. For one, they are very successful at automatically extracting useful features from input data. Just as the weights of a single layer neural networks, the regressions, basically the inputs multipliers, just as those weights were extracted from the data, highlighting features that were more useful than others, similarly, the weights of more complex neural networks are also learned from the data to capture useful features from the inputs. Only that information, from the inputs to the outputs gets intermingled a little bit. But that only makes the neural networks weights more specialized in not only the original features, but also many other combinational features that could be relevant to the target. One popular example would be that neural networks handling image classifications, for example, whose hidden layer neurons would extract from the original pixel information of an image more complex features like edges or curves or patterns in the particular image. And those features, more sophisticated features, are more useful put together for the final image labeling. Now, this automated feature extraction capability of neural networks propelled neural networks into starhood in the recent years, in particular with successes in computer vision and natural language processing. Along with the fact that we have more data and more compute and more sophisticated algorithms to train neural networks, nowadays neural networks power all modern machine learning or AI applications, and as I said, are here to stay, at least for a while. So, how to build and use these powerful machine learning models? Can it be this simple? Specify how many layers you want with how many neurons and what activation you want to choose for those neurons. And by the way, if you like to do some dropout, you can also include that into your script. And yes, it could be this simple. Actually, it is this simple. In particular, with the latest compute and algorithms available to work with neural networks, you can leverage powerful open source so-called deep learning frameworks, like MXNet here, to build models rapidly using only a few lines of code. Previously, keep in mind that getting this neural networks training required researchers to write thousands of lines of codes and maybe wait weeks or days to train them. So let's see how to use MXNet, an open source deep learning library, to train and deploy neural networks by also actually using the API Gluon interface to define and train neural networks much easily. Let's open the Jupyter Notebook for a walkthrough. And let's finally see how all works together on our in-class review dataset to predict the label field. In the current notebook, we're going to go for exploratory data analysis on our dataset, splitting dataset into training and test sets, data balancing, numerical processing, categorical encoding, and text vectorization, all the data processing, train a neural network with MXNet Gluon, and check the performance metrics on the test set. So let's open the Jupyter Notebook for a walkthrough. We can only cover so much in this accelerated dive into machine learning, so check out the open source textbook Dive into Deep Learning at d2l.ai, Amazonian's attempt to make machine learning, and in particular deep learning, approachable in Jupyter Notebooks. So let's introduce another ML technique that's gaining more traction these days, AutoML. AutoML helps automating some of the tasks related to machine learning model development and training, such as pre-processing and cleaning data, feature selection, ML model selection, and hyperparameter optimization. AutoGluon AutoML is an open source AutoML toolkit created by Amazon AI. It's easy to use on tabular data, image data, and text data sets for either all of these tasks: image classification, object detection when you work with different image data. With just 3 lines of code, you can start right away using AutoGluon on make predictions on your particular data sets. In this particular 3 lines of code, we're using the tabular prediction as task. We just give the CSV file. We pass the CSV file to AutoGluon, pointing towards the column which contains your label. AutoGluon, by the way, doesn't have to know if it's you don't have to tell AutoGluon if it's a regression or classification problem. It will figure it out by itself by looking at that label column. And in these 3 lines of code, you're basically training and make predictions on your desired data sets, on your training and test data set. So let's open this Jupyter Notebook and see how AutoGluon works hands-on.